Hello, everyone. This week, we will talk about a new topic, retrieval-augmented generation, RAG. This is our agenda. We will start with the definition of RAG, why we need RAG, and the common pipeline of RAG. We will then dive deep into some technical details of RAG, including text embedding, positional encoding, and vector database. And last, we will talk about how RAG can go wrong and some evaluation frameworks of RAG. Back to our course roadmap, RAG is one of the commonly used techniques to achieve model adaptation. In the previous weeks, we have seen the power of foundation models through tons of examples. However, we also need to recognize the limitations of these models. First, their knowledge is static and is frozen at the time of their last update. This might be a problem in many situations, especially in fast-moving fields like technology or finance. These models cannot integrate new information once they are trained, leading to outdated or incomplete responses over time. There's another problem. The foundation models generally don't know specifics about your private or corporate domains because their training is on public data. This is where RAG comes into play. It allows a model to pull in external, up-to-date data in real time. Imagine you need a business forecast based on the latest market trends from just a few days ago. A traditional foundation model wouldn't know those trends, but a RAG-enhanced model would pull this fresh data to deliver a more accurate forecast. The idea of RAG was proposed by this paper published in 2020. This paper describes the theoretical working mechanisms of RAG. The RAG system combines two key components, a retriever and a generator. The process begins with the query encoder, which translates your question into a query. This query is then used to fetch the most relevant documents from a vast database. Once the top documents are selected, the generator steps in. It looks at the information from these documents and constructs an answer. This entire process involves backpropagation, which is a method used to fine-tune the answers by adjusting the system based on the errors it made in the past. So you might think, wow, that sounds really complex and comprehensive, isn't it? Is this really how RAG is done in practice? Actually, no. While this detailed setup is academically sound, it is usually overkill for most practical applications. In reality, deploying a system that continually fine-tunes every part is often not feasible. It is resource-heavy, costly, and can be over-engineered for everyday needs. In many real-world scenarios, RAG systems use pre-trained components without further fine-tuning. This means they rely on the broad capabilities of the models as trained without making ongoing adjustments. Why? Because it balances performance with efficiency and stability, which is crucial in production environments. This is a general process of RAG. Let's break down this process step by step. First, everything starts with you, the user. Imagine you have a question, maybe something complex, like needing advice on a legal contract. You input your query into the system, asking for specific insights. Now the magic begins. This part is the retrieval model. Think of it as our AI's first tool for digging up information. What it does is pretty cool. It searches through a massive library of documents to find those that are most relevant to your question. It is like using a superpowered search engine that knows exactly what you're looking for. Can you guess what happens after the system finds the right documents? Any ideas on how it uses them to answer your question? After the retrieval model picks out the best documents, it hands them over to LLM. This is where our AI turns from a detective into a lawyer, analyzing the information. This LLM has been pre-trained on a massive dataset before it ever gets your question. This training means it's already learned a lot about a wide range of topics, and now it uses that knowledge to understand the specifics of the document it just received. With the information from our retrieval model and its own training, the large language model crafts a response. So why is this important for you? Imagine using this in real life. Whether you are a lawyer reviewing contracts, a doctor looking up medical information, or even a student researching for a thesis, RAG can provide tailored, expert-level responses based on the very latest information available. So let's talk about the RAG pipeline. Imagine you are asking a question like, how many parameters are there in Grok 0? Now, the first step follows exactly what we talked about with prompt engineering. You input a query just like before, and the prompt template kicks in, setting up the structure of how to represent that query to your model. The LLM processes the input and gives us an answer. That process on its own is great, but sometimes the model may not have all the information it needs in its current training. So what do? We bring in external knowledge from sources like documents or web pages. That's where the unique part of this pipeline kicks in. Look at this black box. This represents a journey that we process the external information and pull in the most relevant pieces. This retrieved information is then brought back and integrated into the original query via the prompt template, helping us create an even better, more informed answer. Today, we will open up that black box and dive into some of the key components inside, or as we call it, the retrieval model. What happens in here is actually a process that transforms raw external information into something useful for our large language model to work with. Let's walk through this process together, step by step. The first step is to split into chunks. Imagine you have big, long documents, maybe a research paper or a web page filled with text. For our model to handle it, we first need to split it into smaller, manageable chunks. Why? Well, it's like trying to remember a book. You wouldn't memorize every page in one go. Instead, you break it into sections, paragraphs, or even sentences. Similarly, we break down the documents so that each chunk is small enough for the model to process efficiently, but still contains meaningful information. This makes sure that we are working with bite-sized pieces of data. Next step is embedding. Each of these chunks go through a transformation called embedding. Remember, our model doesn't understand raw text the way we do. So these embeddings are like a special code, a vector representation that turns the text into something the model can read and understand. Think of it as translating the language of humans into the language of machines. The embedding step encodes not just the words themselves, but also their meaning and context, so the model can later search and compare them effectively. Step 3, vector database. Once we have these embeddings, we store them in something called a vector database. You can think of this as a high-tech filing system for all the chunks we've created. The vector database is special because it allows us to quickly search through all the chunks of data by comparing the embeddings. So when a user asks a question, the system can quickly identify which chunks of information are the most relevant to the query. Finally, after searching the database, we pull out the top results, the most relevant chunks that answer the user's question. The results are combined into a context that will be sent to the prompt template. This context helps the model answer the query more accurately by giving it useful information from the external world. So, to sum it up, the retrieval model, or this black box, takes external documents, splits them into chunks, converts them into embeddings, stores them in a vector database, and then retrieves the most relevant information to form the context. This context is what gets incorporated into the prompt alongside the user's query, making the final answer smarter and more complete. Last week, we explored an example involving question answering with prompt engineering, where we enhance the model's responses by integrating contextual information into the prompts. This method helps guide the model to produce more accurate and relevant answers. However, as you might remember, there is a challenge with this approach. The challenge is the limitation on the length of context we can include due to token limits in the model. Essentially, we can only feed so much information before hitting the maximum capacity of what the model can process at one time. This is where RAG comes into play. Let's think of RAG as an advanced assistant that helps us overcome the token limitation hurdle. Instead of manually selecting and embedding a fixed amount of context into the prompt, RAG uses a retrieval model to dynamically create or generate this limited length context information. It actively searches, processes, and synthesizes information from external documents. Consider you are asking about the latest developments in artificial intelligence. Instead of loading the prompt with a predefined set of data, RAG would fetch the most recent and relevant arguments, extract key details, and use this fresh data to answer your query.